In this video, I will discuss some electrostatics problems from previous year's question papers of JEE Main. This is the first question. On moving a charge 20 coulomb by 2 centimeters, 2 joule of work is done. Then the potential difference between the points is. 4 options are given. You can pause the video and attempt this question. Here is the solution. The work done is the charge Q into the potential difference. This comes from the definition of potential of a point. Potential of a point is work done in moving a unit positive charge from infinity to that point. So the work done in moving a charge of Q is Q times the potential at that point. So the work done in moving a charge from one point to another point is the charge Q into the potential difference between the 2 points. The work done is 2 joules and the charge is 20 coulombs. So from this we will get the value of potential difference as 0.1 volts. So the third option is option 1. This is the next question. A charge particle Q is placed at center O of cube of length L, A, B, C, D, E, F, G, H. Another same charge Q is placed at a distance L from O. Then the electric flux through A, B, C, D is. 4 options are given. You can pause and attempt this question. Here is the solution. So the charge Q is at the center of the cube, and also this charge Q, if you assume another imaginary cube on the right side, it's also at center of that cube. So the flux due to this charge, due to this on this face, will be 1/6 of the total charge, because there are 6 faces of the cube and all the faces are symmetrically placed from the center. So the charge on the face ABCD due to this left charge Q will be 1/6 of the total flux, that is 1/6 of Q by epsilon naught, and the charge due to the Q kept outside is also 1/6 of the total flux from this right charge, that is 1/6 of Q by epsilon naught. But the direction is opposite. So if you take the first direction as towards right as positive, then the flux due to the right charge will be negative. So the net flux will be 0. Another way of getting this answer is the electric field at any point on this face ABCD will be parallel to the face. Suppose I take a point on this face, the electric field due to this Q will be in this direction, and the electric field due to this outside charge Q will be in this direction. So the net electric field due to these two charges, the normal component will cancel. So this electric will have 2 components, one like this and one vertically upwards, and due to the outside charge it will be inward in the left direction and vertically upwards. So the net electric field due to these 2 point charges on this face ABCD is parallel to the face, so there is no electric field cutting the face. So the electric flux coming out of this face is 0. So this is another way of getting the answer. So the correct option is option 2. This is the next question. A thin spherical conducting shell of radius r has a charge Q. Another charge capital Q is placed at the center of the shell. The electric potential at point P at a distance r by 2 from the center of the shell is. 4 options are given. You can pause and attempt this question. Here is the solution. So this spherical shell has got a charge Q. It's a conducting shell. So all this charge will be on the surface, and capital Q is at the center. So you have to find the potential at this point. So the electric field due to this charges at a point outside will be K into Q plus Q by R square into R cap. The electric field due to this point charge is KQ by R square, and electric field due to this charge distributed on this shell is equal to point charge for points outside. So it is Q plus Q by R square into R cap. Inside, the electric field contribution from this shell will be 0. This is a standard result we are using here. So the electric field will be only due to this capital Q present at the center. So electric field inside is K into Q by R square into R cap. And potential at the point is work done in moving a positive charge, that is integral E dot dr minus, so from R equal to infinity to R by 2. So we can split this integral into two parts, infinity to capital R and capital R to R by 2. So from infinity to capital R, the electric field value is Q plus Q by R square, and inside is Q by R square. This is a simple integral minus 1 by, so we put the limits and simplify. We get the final answer as 2K capital Q by R plus K small q by R, and K is 1 by 4 pi epsilon naught. So the correct option is option 3. This is the next question. Two spherical conductors B and C have equal radii carrying equal charges in them, repel each other with a force F when kept apart at some distance. A third spherical conductor having same radius as that of B but uncharged is brought in contact with B, then brought in contact with C, and finally removed from both. The new force of repulsion between B and C is. 4 options are given. You can pause and attempt this question. Here is the solution. So initially the two spherical conductors B and C have charge say Q, and this third spherical conductor A is brought in contact with B. So since it's identical, the charge will get split into two parts and will become Q by 2 and Q by 2. And second contact is between this A and C, and the total charge before touching is Q plus Q by 2, that is 1.5 Q, and after touching and separating, the charge will get split equally between the two. So 1.5 by 2 is 0.75, that is 3 by 4 Q. So after this second contact and separation, the final charge on B will be Q by 2, on C it will be 3 by 4 Q, and on A it will be 3 by 4 Q. So initially the force of repulsion between B and C is K into Q square by D square. Q is the initial charge, and after this contact and separation, the force of repulsion will be Q by 2 into 3 by 4 Q by D square. So it is changing by a factor of 3 by 8. So the correct option is option 4. This is the next question. A charged particle Q is shot towards another charged particle capital Q, which is fixed with a speed v. It approaches Q up to a closest distance of small r and then returns. If small q was given a speed 2v, the closest distance of approach would be. You can pause and attempt this question. So this problem can be solved by energy conservation. So the loss in kinetic energy will go in increasing the electrostatic potential energy. So the loss in kinetic energy in the first case, when it is projected, the velocity v is half mv square, and that goes into building the electrostatic potential energy, that is K product of the charges divided by the distance. R is the closest distance. So at this closest distance the velocity is becoming 0. In the second case, when it is projected with velocity 2v, the loss in kinetic energy is half m2v square, and let the closest distance of separation be r1. So dividing these two, we get r1 by r ratio as 1 by 4. So from this r1 is r by 4. The correct option is option 4. This is the next question. 4 charges equal to minus q are placed at 4 corners of a square and charge small q at its center. If the system is in equilibrium, the value of small q is. You can pause and attempt this question. Here is the solution. So the 4 charges minus q are placed at the corners of a square, and a small charge minus q is kept at the center. So since the system is in equilibrium, the force on any charge should be 0, the net force. So let me take this minus q at this right bottom corner. So the net force acting on this minus q due to the other 4 charges should be 0. So this minus q will repel, let that force be F1, and this minus q will repel in downwards direction, and the magnet will be same F1, and let F2 be the force of repulsion because of this minus q here. The magnet will be different F2, but it will make a 45-degree angle with this F1, and q will be of opposite sign so that it gives an attractive force which will balance this F1 and F2 combination. So let that force be F3, and that will act at an angle 45 degrees with the vertical. So the F3 should be equal to F1 into root 2, because the combination of F1 and F2 at an angle of 90 degrees will be F1 root 2, and F2 is acting in the direction opposite to F3, so it is just plus F2. F3 is between Q and Q, so Q cubed by the distance square, the distance in center, and the corner is A root 2. The side of the square is A, so the distance of the diagonal is root 2 times A, and half the diagonal is A by root 2. And F1 is Q square by A square into root 2, and F2 is Q square by the distance square, and distance is the diagonal, which is root 2A square. So simplifying, we get small q as capital Q by 4 into 2 root 2 plus 1. So the correct option is option 2. This is the next question. A charged ball B hangs from a silk thread S, which makes an angle theta with a large conducting sheet P, as shown in the figure. The surface charge density sigma of the sheet is proportional to. 4 options are given. You can pause and attempt this question. Here is the solution. So we have to draw the free body diagram of this ball B. So the force acting on this ball will be the weight mg vertically downwards and the tension of the string, and there will be electrostatic force due to the charge on this sheet and the charge of this ball, and that has to be a repulsive force, and that force will be Q in the electric field. The electric field due to the surface charge density sigma is sigma by 2 epsilon naught. This is a standard result we are using here. So now writing the force balance equation in the vertical direction and the horizontal direction, we get T cos theta equal to mg and T sin theta equal to Q into sigma by 2 epsilon naught. We can eliminate the tension by dividing these two. So we get tan theta equal to Q into sigma by 2 epsilon naught divided by mg. Q, the mass or constants. So sigma is directly proportional to tan theta. So the surface charge density is proportional to tan theta. So if the surface charge density is more, then the angle of repulsion will be more, so theta will be more. So the correct option is option 4. This is the next question. 2 point charges plus 8q and minus 2q are located at x equal to 0 and x equal to L respectively. The location of a point on the x-axis at which the net electric field due to these 2 point charges is 0 is. You can pause and attempt this question. So the charge 8q is placed at x equal to 0 and minus q at x equal to L. So somewhere the electric field is 0, so we have to find that position. If you take a location right of these two charges, the electric field due to 8q will be towards right and electric field due to minus 2 will be towards left, so it's possible to cancel somewhere here, but in between the electric field due to 8q will be towards right and the electric field due to minus 2 will also be towards right. So it's not possible for the electric field to become 0 in between the two charges. So electric field at point P, let us assume the coordinate of that point P D is k into charge 8q divided by the distance square, and the electric field due to this minus q will be in the opposite direction. So that will be minus k into 2q divided by the distance square, and the distance, this distance is d minus L square. So from this we get 4 by d square equal to 1 by divided by d minus L square. Taking square we get plus and minus sign. So we get two values of D. There is simple calculation. So D is 2L or 2/3 L. 2/3 L is in between the two sizes, which is not possible. So the correct answer is 2L and the correct option is 1. This is the next question. Two thin wire rings, each having radii R, are placed at a distance D apart with their axis coinciding. The charges on two rings are plus Q and minus Q. The potential difference between the centers of two rings is. You can pause and attempt this question. So the left ring has a charge plus Q and the right ring has a charge minus Q, and they are separated by a distance D and the axes are coinciding, so it's like this. The potential at this point P is due to this charge Q and also due to this charge minus Q. So all the elements of this charge Q are at a distance of R from this P. So the potential due to this ring of charge Q will be K into Q by R, and all the elements of this ring of having minus charge are also the same distance from this point P, and the potential is a scalar quantity and the distance is square root of D square plus X square R square. So the potential due to this minus Q will be minus K Q divided by the distance R square plus D square. The potential at point Q is potential due to this plus Q and potential due to this minus Q. So similarly, the potential will be minus KQ by R, because all the elements of this minus Q are distance R, and all the elements of plus Q will be at the distance square root of R square plus D square from this point Q. So plus KQ by this one. So you have to find the potential difference. So Vp minus Vq, so it will become twice of this one, and K is 1 by 4 pi epsilon naught. So putting that, we get the potential difference Q divided by 2 pi epsilon naught into 1 by R minus 1 by square root of R square plus D square. So the correct option is option 2. This is the next question. An electric dipole is placed at an angle 30 degrees to a non-uniform electric field. The dipole will experience a translation force only in the direction of the field. Option 2, translation force only in the direction normal to the direction of the field. Option 3, a torque as well as translation force. Option 4, torque only. You can pause and attempt this question. So the dipole is made up of minus Q and plus Q. Since the electric field is non-uniform, the electric field at this point will be E1, and here will be different, to be E2, and let the directions be towards right. So the force acting on this plus Q will be QE1 towards right, and acting on minus Q will be QE2 towards left. So the net force is QE1 minus QE2, and since E1 and E2 are not same, there will be net force acting on this dipole, and also there will be a torque. So there will be torque as well as translation force. The correct option is option 3. This is the next question. Two spherical conductors A and B of radii 1 mm and 2 mm are separated by a distance of 5 centimeters and are uniformly charged. If the spheres are connected by a conducting wire, then in equilibrium condition, the ratio of magnitude of electric fields at the surface of spheres A and B is. You can pause and attempt this question. So the potential of this sphere A due to the charge QA present in its KQA by RA. Here assuming that the charge is uniformly distributed, and that's given in the question. Similarly, the potential of the spherical conductor B is K into its charge QB divided by its radius RB. And once they are connected by a conducting wire, the potentials will become equal, and there will be redistribution of charges, and let the charges be QA prime and QB prime, but the potentials will become equal because they are connected by a conducting wire. So in that case, QA prime by RA will be equal to QB prime by RB. Now the electric field on the surface of A due to the charge present in A will be K into QA prime divided by RA square, and similarly to sphere B will be K into QB by RB square. we are continuing to assume that the spherical conductors are uniformly charged. So the ratio of the electric fields will be in the inverse ratio of the radian. So it will be 2:1. The correct option 3.